So here's an example that actually involves a bit of actual differentiation. So the volume expended or released from a typical hydroelectric power station naturally decreases. The volume mathematically is given by the volume over time is 175,000 e to the minus that t, where t is in days from first opening. So first, the power station opened in 2010. In what year will be half of the expended volume of water? The year of expending is that, find the flow rate, and then state a reason why the model is not very accurate. So go ahead and give this problem a try, and when you're ready, you can come back for the solution. So I'll just rewrite the volume again. So it's 175,000 e to the minus 0.12340 is 4t. We're told then that t is 0. Well, the initial volume would be 175,000 if you plug t of 0 into there. What we want is half the volume, which is 87,500, I think. Let me just gotta double check my quick maths here. Yeah, 87,500. So obviously that 87,500 is going to come down and divide by that. So we'll get a half is e to the minus 4t. So once we take the natural log, this natural log of a half can be turned into minus log 2 is minus 0.12344t. So to use natural log of 2, 0.1234, which is 17,328. T is in days. So if you want to get it into years, we divide by 365, which is 47 years. Now, it opened in 2010, so 2010, adding another 47 years, is the year 2057. Just checking my other screen if I have enough room for this. I want to give myself one slide. Okay, so that's the first part of it. It will expend half its volume in the year 2057. Now, the area of expending is 0.01. Find the flow rate of the water at this time. So we want dV by dt, and that's equal to A times V. So dV by dt, when differentiating exponentials, this comes down and we divide. E to the minus 0.224t. And then we're looking for t equals 47. So then dV by dt at t equals 47. 1, 2, 3, 4, and then e to the minus 0.12344 times 47. It does give us a negative answer. Which is kind of expected because we're actually dividing by this, but this is the rate of flow. So at this point, the rate of flow is actually decreasing. So as you can probably tell by the curve formed by this, the derivative is always going to be very much less than 0 because it's always decreasing. So this would be the curve. It's like a typical half-life curve if you've seen any of them. So obviously at any point here, the volume is going to be, or the rate of change of the volume is going to be decreasing. So here, for instance, it's going to be decreasing. At t equals 47 here, it is going to be decreasing, but not too much. But in this case, we do get a very large decrease, which is about, this is quite large, minus 4.3 times 10 to the 9 cubic meters per day, which is quite a lot. Now, the area of expanding, we're told, is 0.01, but we're told to just find the flow rate. So the flow rate is, oops, the flow rate is just minus 4.3 by 10 to the 9 cubic meters per day. Then we're told to comment on why The model's not very accurate. Well, obviously, for large values of t, models tend to get very inaccurate. 4.3 by 10 to the 9 cubic meters per day. If this is water, for instance, the mass of the water would be 1,000 lots of this, which would be 4.3 times 10 to the 12 kilograms of water. Now, just to put that into perspective of how quick that is, if we left the HEP station running all day, every second, every second we'd have 4.97 times 10 to the 7 kilograms of water flowing per second, which is absolutely absurd. So, obviously, with that, we can comment not realistic. Model. And that is the answer to that somewhat complicated flow rate question.